Hi everyone, Mike here. So this week we're going to do something a little bit different. We're in the last couple weeks of the semester. So this week I'm going to talk a little bit about the major types of reasoning and a little bit about logic and logic gates. I'll explain all that in a minute. And then next week will be our final wrap-up week where I'll give you an overriding argument of how I think you should approach critical thinking, once you leave the class. And I'll talk a little bit about the final next week. So for this week, we're going to briefly go over different types of reasoning. You may have run into these before, but in philosophy, logic and reasoning have specific definitions. Of course, in philosophy, everything has a definition, so that shouldn't be surprising. And there are three main types of reasoning. And so the first we're going to look at is called induction. Now, induction is pretty easy to remember. They're all a little bit kind of easy to remember. And it's something that you probably have used many times in your daily life. You just didn't give it a name. And so the famous example here that you'll see is if you go around the world and look and you see a white swan and you see another white swan and you see another white swan, and then you look around some more and you see a couple more white swans. You might argue white swan, white swan, white swan, all swans are white. The problem with this type of argumentation, obviously, is that way back in the day when they thought that all swans were actually white, and then the British showed up in Australia and saw a black swan. And it turns out there are black swans. So this is a very powerful type of reasoning, and it's very common. We use it all the time. Is you get a piece of evidence, another piece of evidence, a repeated piece of evidence, and you start to draw a claim, which is okay as long as you limit the claim. The weakness of this type of inductive argumentation is that you can never really make a universal claim. Now, people do it all the time. The sun came up 10 years ago. The sun came up 5 years ago. The sun came up 1 year ago. The sun came up yesterday. Therefore, the sun will come up tomorrow is an inductive argument. That's a bad argument. It's probably true. It's almost certainly true. I hope it's true that the sun will come up tomorrow. But it's not perfectly true. Something weird could happen. The Earth could be destroyed. The sun could be destroyed. It could turn out we're living in a computer simulation and they shut it off. Many things could happen. And so this type of argument is limited by the constraints that you put on it and limited by the amount of evidence that you have. But the key to remember with an inductive argument is no matter how many white swans you've seen, one single black swan defeats the universality of that argument. Okay, so that's an inductive argument. White swan, white swan, white swan, black swan. Okay. The second most famous type of reasoning is called deduction. Now, a deduction is something that you've also probably used many times in your life. You make some kind of general, large-scale claim. So Socrates, I'm taking he said men, not people. I'm trying to modernize it a little bit. So Socrates is going to make a general claim. All people are mortal. Socrates is a person. Therefore, Socrates is mortal. Now, this is a very, very strong type of argumentation. It goes from the general to the particular, general to the specific. And if you argue it carefully, it's almost always right. Now, it's limited. We'll talk about it in a minute. It's very limited because you have to have a careful setup of the general and a careful setup of the particular for it to be a strong argument. But when it's set up properly, it's a very, very strong argument. Socrates is almost certainly going to die. As far as I can think, he's definitely going to die. And we know he did die. And the same thing is true of all of us. All people are mortal. You and me, we're people. Therefore, we're mortal. Okay? That is a strong argument. That's a deductive argument. It goes from the general to the particular and then gives you some type of conclusion based on those two things. Okay? Now, the weakness of this type of argumentation is that it can be valid through argumentation, but not really true in real life. So, for example, I got a good example for you here. All philosophers are good looking. Obviously, all philosophers are good looking. Mike, me, is a philosopher. You could finish it, right? If all philosophers are good looking, Mike is a philosopher. It follows from the necessity of the structure you've set up that Mike is good looking. but you should see the weakness of this type of an argumentation. The form of that argument is strong, the form of that argument is perfect, but the actual conclusion doesn't match real life. I'm basically average looking. And so that is just how has a very strong place in argumentation if it's used properly. But once you try to stray outside of the theories and the particulars that clearly follow for that theory, it can run into problems. Okay, so the first was inductive argument, swan, 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 black swan. The second is deductive arguments, all people are mortal. Socrates is a person, therefore Socrates is mortal. And our final version, our final type of argumentation is called abduction. Now there's a couple of types of abduction. I'm just going to talk about one of them. So abduction is sometimes called inference to the best explanation. And the way this works is, so imagine you went to bed and your sink was clean. And when you wake up in the morning, you walk out into the kitchen and you look and you see this. You see a sink full of dishes and pots. And you go, I'm guessing my roommate or my spouse or whoever happens to live with you got up in the middle of the night and made a giant meal and then left all the crap sitting in the sink. Okay. Now this is your best guess, really. It's an inference to the best explanation for the evidence that you have in front of you. Now, it could be that, Bigfoot broke into your house in the middle of the night, wanted to trick you into guessing that your roommate did it, took a bunch of stuff, and then Bigfoot put it inside your sink. Now, that's massively unlikely. Okay? Bigfoot probably did not break into your house and put stuff in your sink. Okay? And most of us know that. So it's a type of argumentation that we use all the time. We have limited evidence, and then we give our best guess based on that evidence. Its main weakness is really, it's just a guess. It's really just a guess based on some type of evidence. It gives you a probability at best. It can never be 100%. Okay? And so this is the third type of argumentation. Now, in your daily life, you've probably run into these many, many times. Inductive arguments and abductive arguments especially show up everywhere in our lives. And even deductive arguments show up pretty regularly. You'll see something in life that's a big, general type of a thing. I don't know, in my family, everybody gets together every Christmas is a general argument. So, will Mike get together with his family this Christmas? Yes, probably. It follows from that. Okay, so that's the type of a deductive argument that you would use. It's not as strong as the example I gave, but it's similar. And that we also use in daily life. Okay, so these are three main types of argumentation, and for the assignments this week, you can either pick this or one of the other sections. But if you pick this, just try to think in big scale types of reasoning. Don't get too caught up on the little details. Okay? Now, as I said before, philosophy has this very specific meaning for logic. Now, we're not going to do any hard scale, any very, very difficult levels of logic in the class. We're really just it's going to be limited to this day, but I thought I should just very briefly explain to you. If you decide to go on and do more logic classes, or perhaps you are interested in computer science, many people who do computer science will do a logic class as well. I did logic classes. It's required if you want to get a PhD in philosophy. So I did these. It's been a while, but I liked it. I enjoyed it while I was doing it. And it has a specific place in philosophy, but it's very hard to apply broadly. So the example I'll use later on will be a little more broad, and I'll explain to it when we get to it. So what you're looking at here is called modus ponens. It's the most famous and probably the simplest of the logical arguments that you learn in symbolic logic, or sometimes called propositional logic. So what you have there is a little horseshoe symbol, and that little horseshoe symbol means if, then. If, then. And sometimes it's represented by an arrow, which I'll show you in the next slide. And so it reads like this: if P, then Q. So what that's saying is that little symbol represents the relationship between P and Q in that first line. That's the first premise. If P, then Q. P. So the next line is saying what the actual state of the affairs is. You're getting P. And so then the answer for if P then Q, P is Q. And so a way to a famous example I learned when I first took logic class was, if it's going to rain, I take my umbrella. That's if P then Q. If it's going to rain, I take my umbrella. It's going to rain, therefore Q, I take my umbrella. Now this is a very famous and powerful type of argumentation. You've probably used it a million times. We use if-thens all the time. And in philosophy, if you take a full-scale symbolic logic class, you will take this type of thing and build it into much longer types of argumentation with different types of symbols and different types of connections between the symbols. It'll look something like this when it gets longer and bigger. So this is 7 lines. I think I'm trying to remember back, this is many, many years ago now. I think 15, 16 lines was about the most we ever got up to for a problem, a logic problem. And so we got 7 lines here, and it looks something like that. And so what you have, this is the first line, you use different rules to move deductively from step to step to step to step. Okay, and you learn the rules and then you proceed from there. Now, so just so you've seen this, if you are interested, one of the assignments this week is to go look at this a little bit more. You can if you want. That's also a choice. So there's 3 choices, like usual. This will be one. Okay, so if you want to go down that road, that's the very, very basics of where that'll take you. But finally, I'm going to have you look at this. So what we have here is what are called logic gates. Now, a logic gate is a lot like the if-then. There's various versions of them. If you've ever taken a computer science class or some type of electronics class, some of this might seem familiar to you. I did a little bit of electronics. I learned how to read diagrams, stuff like that, many, many years ago. So let's look over here at the far left of the screen for a very basic one. So what we have here is what's called the input. And what we have here is called the output. I need my glasses, these are too little. Okay. So what we have here is the input, and what we have here is the output. And it's a lot like the if-then we just looked at. So if I switch this from off to on, it lights up. Okay. If I don't, it doesn't. So this is an if-then. This is an if-then right here in logic gate. Now you might say, what the heck is a logic gate? What purpose does this have in my real life? These things are everywhere. Every cell phone, every computer, almost every type of electronic item. Many analog items have some version of a logic gate in them. I'm going to talk about a password in a second. I'm going to talk about a doorbell in a house. All of these things work on this type of reasoning. Okay, these are everywhere around us all the time. All of your computers are basically thousands and thousands of little logic gates built into them. That's how they add up numbers or subtract numbers or whatever it is they're doing. Okay, and we're not going to get into those details. We're just going to run through a few of the basic things. So just like we saw with if P then Q, it's if power, then it comes on, then lights up. Okay, it's very simple here, if then. Now there's various operators you can use. So there's an operator called and. And so instead of it being just if then, like this one is, it's if then, and. Okay? So if I turn on this one and I turn on this one, then we get the light. That's what the and right here does. It has its own little special symbol. Okay? If I only turn on one of them, it doesn't work. Okay? It doesn't work. It's got to be both. That's what the and does. Okay? So if I turn on this one, nothing happens. If I turn on this one and the other one, it comes on. Okay? That is a logic gate right there. Okay? Here's another type of logic gate. This one's called or. So I can turn on this one and it comes on. Or I can turn on this one and it comes on. Or I can turn on both of them and it comes on. Okay. Now this might seem a little bit weird and obscure and you're like, oh, Mike, what the heck purpose of this? So the main purpose here is to think in a visual way about logic. So in the same way I talked about if it rains, I'll bring an umbrella. This is the same type of thing. If you do certain operations in one way or another, then a certain outcome will happen. Okay. And this is the type of logic that you see in daily life all the time. So this one is a lot like a doorbell in a house, the OR. So many people have one ringer in their house that's a doorbell, but they have two buttons. There's a button outside the back door or the side door and a button outside the front door. And if you push the one, it rings the doorbell. If you push the other one, it rings the doorbell. I guess if somehow they were both pushed at the same time, it would probably ring. I don't know, I've never tested that, but that's probably what would happen too. Okay, so this is something you see all the time. This is a thing you see in daily life all the time. Okay, now one complication, if you decide to pick this one you can mess around with, is called the not. The not. And what a not is a negation of the earlier thing. So you can take a little thing like this. I've tested this out on phone. I've tested it out on computer. You can try this out if you want. It's kind of fun to play around with if you're that kind of a person. So remember with this one before, I had to do this one and this one to get it to come on. But you'll notice right now that it's already on. Okay? So what the not does is it makes the opposite of what you had set up before. So this one, if I want to shut it off, I got to turn these both on. And if I turn them both off, it comes on. Now this one is how many alarm systems work. Okay? If somebody breaks the circuit, then the alarm goes off. Then the alarm goes off. It's kind of like in a constant state of pause all the time. Like if you do nothing, nothing happens. But as soon as you break the window, then the thing happens. Okay? So you have the alarm, it's on right now. Nothing's blaring out. Okay? Somebody breaks the thing, you get an alarm. Okay? So that's how that not can work. That's how that not can work. Okay. Let's do one more. Some of them can be combined. So you can take an and or an or and you can negate it built in. So you look down here and you'll notice that this symbol looks a lot like the other symbol, but it has this little dot on the end of the circuit. And so what this does is it also does the opposite, but it does the opposite of the and, okay? So you'll see that you have to turn both of these off to get it to come off. So it's a not and, it's a negation of the and, okay? And there's a couple more. If you're interested in this, you can look at them and play around with them. I want to take you through one little real life example so you can see how complex these can get, and you can build one and take a screenshot for your assignment if you want. So up here, this is not exactly how it would work, but it's close enough to explain. Up here is what you would get with a password. So imagine that this is one number of your password, this is the second number of your password, this is another number, and this is another number, okay? So if you have power, you know, to the ATM or to, I don't know, the little thing at the grocery store where you have to put in your card number if you do that with your debit, you have to put in your number. Now, let's say you're one of the millions of people who has the really bad password of 1234. Believe it or not, people do actually do this. If you ever need to hack something, try that. It'll probably work. 4321 might work too. But let's say you're one of these people who has 1234. Now, you have to put in every single number correctly. If you don't, the output won't come on. If you put in 1, you put in 2, you put in 3, and you put in 4, it gives you the money or it runs your card or whatever it is you're trying to do. If you get one of them wrong, if you put in 1, 2, 5, 4, it doesn't work. It kicks you back into the system and says password wrong. This is how that works. Millions of things are like this. Every time you sign onto the website for the class and you type in your password, if you get your password wrong, that's what happened. This is what happened. It's a complicated system of ands and ors and if-thens built into the computer. And these kinds of things are everywhere around us, all right? And really, it's exactly the same as the symbolic logic that you learn if you take a symbolic logic class. The symbols are different, and maybe it's not quite as practical. But really, underlying it is the same types of things. It's a series of operators, a series of actions that happen if those operators work properly, and it's a series of negations of those operators. The ands or the ors or the nors and the nans, stuff like that. Okay? So, for this week, you have 3 options to go from. You can talk about and look at, read the little assignment for the big scale types of reasoning. So that's induction, deduction, and abduction. Or you can, if you're really brave, go look at a little bit into propositional logic, symbolic logic. Or if you're like a more practical, kind of a fun computerish type thing, you can come play with this app, which I'm giving you the link for there. You can build your own circuit and explain it to me, take a screenshot or take a picture with your phone and send it in, okay? So logic is really underlying many parts of our lives. Usually we don't think about it, like many things in philosophy are present in our daily lives, but we don't think about them a lot. And logic is one of those things. The world is literally running on it right now, all the time. Okay, so for this week, those will be your 3 assignments based on one of these 3 sections of this quick lecture I've given you. Okay?